You guys work on anything else? After you get go back on the phone.
And then make some jigs, 3D print some. Keep our cuts straight.
You guys just kind of like free-handed then?
We're gonna use a hand saw, but we're gonna try, like I said, we'll try to make a jig to keep the cuts as straight as possible.
Sure.
We took it to the machine shop and John's like, yeah, you can pen that in here.
Yeah,
So
it's on.
it's hardly lasting.
It's good at vacuum, it's good, I said vacuum and vacuum. It was like that.
I'm pretty sure a few years ago they cut it.
Yeah, maybe not bad.
I think it's just.
So, he probably was gonna cut it, and then he's gonna. I was about to download, you should not put that in, we're getting your eye and cut it.
Put a mask on, it's very close. Have a mask on. We're doing a hand saw, so it shouldn't cut, I mean, it's not gonna.
It's on a flyer.
Yeah,
It's
it's on-
usually like mechanical saw,
Yeah.
yeah. With-
A power saw, cut it
This
fast
is a
enough
chain
where,
saw.
yeah, so it should. There's a chop saw in the shed that. I guess, but
I got a plan, I cut it this Thursday.
I try to 3D print some stuff. Dylan said he was gonna like make a jig. I doubt it, he was talking to. All souls, yeah.
And now it's I pick up the last of the popcorn.
Oh, you did?
Not these, but not mine. But He's just doing gigs, he's looking at all and shit. Like,
See, you know, we like.
you know, I did.
No, it was just a good general shout, there was something about batteries.
Sure.
It says can't use LiPo unless it's a LiPo run from some mega
Well, they are,
featherweight, so like,
they are providing.
it's either provided, like installed.
I was gonna mention when we had a lot. Do you still want to do this, right? No, I think that's supposed to tell you about it. Shit on the side.
No, that's fine, like, so I don't even, because David has like shown any, I messaged him, but it's. He didn't show the, like, kind of that confidence for me to think.
And I don't think it should happen, really. Like I said, I don't know if it should be on it, or I think we should focus mainly primarily. So, yeah, and I feel like the safest option is gonna be when we have commercial shells to do it.
So I agree.
Yeah. Well, you did that for anything.
I didn't take you last night. It's okay,
My phone's on do not disturb.
it's okay, it's okay. I hit this one, but it's fine.
He has your number, text from Kevin muted.
Yeah, I think we should follow roll with that.
Yeah.
We ordered all the computers over.
I put the order in, whether or not to get them. We got an email today, I was super excited, it was a box of screws.
Oh, the wasn't the lock nuts, right?
No, we got the lock, it's just fascinating.
Oh, fab.
Yeah, because then you get the whole $500,000. Yeah. Next time, better go. I wanna try the black sesame. Oh, that one's a good, the food one is good. Yeah, the salad one is good.
Where'd Doug go? Go home?
Yeah. And she wants with
You didn't go. Huh? You didn't go. I actually had my phone in the service. You know what I thought this was? My little move. I thought it was the night mode. That's why you know.
I can't you too.
Does it show? I think I have it set. You should have told me. I think it's told you. Whatever.
I didn't look at that.
You did. You did.
I didn't like.
Oh, what?
No, I eat, work, and then I like the.
All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good. All right, so the plan for today is we're going to continue our lecture notes on lump parameter modeling. So I have another example for you guys. This example, we're going to take another step, and so we're not only going to derive the equations, we're not only going to solve their system in MATLAB, but we're also going to tune the system as well. So we'll talk about what tuning means today, and how do you do it, and why it's important, right? So all of this is in kind of preparation for the next homework assignment. So I posted a couple of new assignments for you guys yesterday. One of them is not really an assignment, it's just a survey. But by this Friday, I want you guys to choose or tell me what type of model that you want to work on for the final project, or I should say the rest of the midterm project and the final project. So remember when we talked about the midterm project, there was a list of different types of models at the end of the document there. So now that you guys have done the tutorial, you guys can, you guys understand Vascular, how it works. You guys can kind of pick the type of model that you want to do. Okay. So there is a poll or a quiz or whatever you want to call it on Canvas right now. So please do that before Friday. And then what I'll do over the weekend is I will email you the image data that you're going to use for your final project. Okay. So just a reminder, so for the rest of the midterm project, what you've done so far is the tutorials, the Vascular tutorial. So that's about 20% of the points for the midterm project. The rest of the 80% of the points are going to be, selecting your model and constructing your model that you're going to use for the final project. Okay, so this is kind of the next step in that process. All right, and then the other thing that I posted yesterday was a problem set. So it is homework officially called homework 2. We're a little bit late in the semester for this to be called homework 2, but here we are, I guess. So on that assignment is basically 3 problems for you to do, 3 circuits for you to do kind of the whole steps. First of all, derive the equations for the circuit. Next step is to solve for their solution in MATLAB. And then the last step is to tune the parameters to get a certain amount of results. Okay, so after today, you should have everything you need to do for homework 2. Today is the last day that I plan on spending on one parameter model. Okay, and so the due date for homework 2 will be next Friday, March 15th. So we have something due this Friday and something due next Friday. So kind of keep in mind for that. Okay. All right. Any questions I can answer before we get started for today? All right. So let's go ahead and get started. All right. So the topic for today, same as we're picking up where we left off last week, which is lump parameter modeling. So just to kind of refresh your memory about what lump parameter modeling is, basically we're using circuits and kind of the analogy of circuitry with all its elements to kind of give us a low dimensional or very quick model to solve for blood flow. Because what we've learned over this semester so far is that blood flow is very complicated. It not only involves fluid mechanics, which by itself, fluid mechanics is already pretty complicated, but we also have things like, deformable walls, unsteady flow, strange geometry. And so, to kind of make it simple for us to give us something that we can solve either by hand or very simply during MATLAB, we're using the circuit analogy to kind of help us out. Okay. So this is kind of, again, this is kind of the first time in this class where we're actually doing some actual modeling. Okay. And again, we're starting with this, or we're kind of starting our modeling journey with this for a couple of reasons. And so on the one hand, it's generally when you're learning something new, starting from the simplest thing is always the best thing to do. But we can use non-parameter modeling in really clever ways as well, and mostly as boundary conditions for other more higher dimensional models. So later on in the class, we're going to go over one-dimensional models, and then eventually we're going to go over three-dimensional or CFD models. And so the lump parameter modeling, or everything that we learn here, is going to be applied for that. Okay. So this unit right here, lump parameter modeling, I spent a bit more time on it than usual, than a typical than when I've learned it, just because it has a lot of applications for a lot of places. Okay. Okay, so let's go ahead and do another example. And so last time we met, last Thursday, we did a couple of examples where I showed you guys a circuit and we walked through the process of developing the equations for that circuit. Okay. So let's do the same thing here. So this circuit here is a bit more complicated. Okay. All right, so we have a circuit that looks like this. And so we have, if I can draw a horizontal line. All right, so first thing we have here is we have an inductor and a resistor in parallel with each other. Okay. And this is the first resistor, so we'll call it R1. Okay. Then they converge and then they split again. And so on the one hand, we have a resistor here. We'll call this R2. That resistor is going to go to ground. And then we also, in parallel to that, we have a capacitor here that's also going to go to ground as well. Okay. So this is a capacitor. Okay. At the inlet of this model, we have our inlet boundary condition. One thing you should always look out for in these circuits is what is the inflow boundary condition. So our inflow boundary condition here is a pressure. So we have PI of T, in this case, is 30 cosine pi T plus 90. All right. So for this circuit here, we're gonna run through the same process that we did before. We're gonna derive the set of differential equations that govern this circuit. So we'll do that part by hand. And then the next thing we're gonna do is we're gonna solve for its solution in MATLAB. Right. So if you remember from last Thursday, we introduced this tool called ODE 45 in MATLAB, which we can use to solve for the solution to these systems. Okay. So I know I went a little bit quickly last time, going over ODE 45. So you'll get to kind of see that in action again today as well, okay, to give you some help. Okay. And then one thing we'll do in addition to this, after we do those two things, is we're going to tune this model, but I'll hold off on that until we get to that point. Okay. All right. Any questions on this so far? Okay. All right. So we have our circuit here, and so let's start with step one of our process. Right. So when we're deriving a set of differential equations for a circuit, the first thing we have to determine is how many differential equations are we going to have in the first place. And to do this, it's fairly simple. So all you have to do is just count the number of inductors plus the number of capacitors that you see in the circuit. And so in this case, we have one inductor and one capacitor. And so that means we're going to have two ODEs. Okay. So pretty straightforward here. Okay. Next step. So I left a piece of information off this circuit on purpose, just because you're going to have to do this for the homework. When you kind of decide how many equations that you're going to make, right? It's good to kind of remember what equations you're solving for each circuit element. Okay. So for each inductor, what you want to solve for is the flow across that inductor. or the flow rate, I guess I should say. And so even if it's not shown to you in the figure, right? So oftentimes, I think for the first two problems on the homework, I give you the circuit with everything that you need and labeled. But oftentimes, you're going to be given a circuit like this where nothing besides the circuit elements, nothing's going to be labeled, right? So what you can do is you can, for each inductor, you can label because you know that you're going to solve for this anyway, right? And so for this inductor, you can see that I've added this QL variable that we're going to solve for, okay? And so just because the circuit doesn't give it to you, and so you can add these variables on yourself, just because you know that every time you see an inductor, you want to solve for the flow rate. So add this if not there. Okay. All right, similarly, for each capacitor, for each capacitor, we're going to obtain an equation to solve for the pressure on that capacitor. Okay. And so we come back up to our circuit right here, right? We have our capacitor here in the bottom right. And so we need to label where that pressure is going to be. Okay. Placing the pressure is if you kind of understand circuits, it's simple. But if you're not used to looking at circuit diagrams, it can be a little bit challenging, right? Remember that everything connected by a wire, it has the same pressure, or has the same voltage, right? And so I'm going to put this pressure here, right at this junction, right where it splits. But know that this pressure is applied to everywhere connected to this by a wire. Okay. It's only when you travel across a resistor or across a circuit element does the pressure change. Okay. So everything that I've highlighted in purple here in the circuitry is at the same pressure. And so technically you can label this anywhere because all of that's going to be at the same pressure. But just for the sake of argument, I'm going to put the pressure right here at that junction. And so we'll call this PC, okay, for pressure on the capacitor. Okay. So just a little note so that if the circuit doesn't tell you kind of these variables that you should be solving for, you can add them yourself. And in fact, you can actually label them yourself too. Okay. For this problem, we just have one inductor, one capacitor, so I call it QL and PC. Okay. All right. So now that we know what we're solving for and kind of where they're located in the circuit, let's go ahead and write their equations. Okay, so let's start with the inductor equation. So the inductor equation, just to kind of refresh your memory, we're going to dQL dt is equal to 1 over L times the upstream pressure, or the pressure that's upstream on the inductor, minus the downstream pressure. Or if we have our inductor like this, right, L, QL flowing across. The upstream pressure is just whatever pressure that the inductor sees or the inductor feels kind of on its left side. Okay. I say left side, but it's just wherever the flow is coming from. Right? So this right here is P up. And then the downstream pressure, P down, is just whatever pressure that the inductor feels on its backside. Okay. Okay. P up and P down. And so to get our inductor equation, we need to look at our circuit and then plug in for what we observe as P up and P down. All right. So let's go back to our circuit diagram up here. Right. Let's locate our inductor. So our inductor is, let me use blue. Right. Our inductor is right here, kind of in the top left of the circuit. Right. So in this case, the blood is flowing from left to right. going to go from the inflow to ground, right? So the upstream side in this case is on the left. And so the upstream pressure in this case, if we follow this wire, right? Remember, everything connected by a wire is at the same pressure, right? Since all of that area there is connected by the same wire, we know that the upstream pressure here is Pi of T. Okay? And so in this case, P up is equal to the inflow condition Pi of T is equal to 30 cosine of pi t plus 90. Okay. All right. P down. So the pressure on the downstream side of the inductor is everything that's in purple, right? And so actually the downstream pressure on the inductor is going to be the same as the pressure on the capacitor, right? Because it's all connected by a wire. So P down is equal to PC. Okay, so let's plug these in. So you have dQL dt is equal to 1 over the inductance multiplied by quantity. Upstream pressure, 30 cosine of pi t plus 90 minus P sub C. Okay. We don't know what P sub C is at the moment because, you know, that's what our other equation is going to be, right? Remember, when you create these systems of differential equations, oftentimes you're going to have these equations are going to be coupled. So the solution of one equation depends on the other. So it's very common. In fact, it's basically expected that you should have some coupling between these equations. Okay. All right. Any questions on that? Have we got that equation there? Okay. Okay, so that's the inductor. All right, so let's do the same thing for the capacitor, right? So for the capacitor, the way that we obtain our equation is through conservation of mass, or in other words, Kirchhoff's current rule. And in fact, what you're actually doing, to be more specific here, is we're going to apply conservation of mass to get an equation for the flows going into the capacitor. So usually what this means is that you're going to apply conservation of mass at a junction that's nearby the capacitor. Okay. Let me show you what I mean. And so let me draw the circuit here again, just for the sake of just to make it a little bit easier, so we're not scrolling a ton of times. Okay. So that's our circuit. Let me label the elements L, R1, R2, and C. Okay. In each of the 4 branches here, we're going to have a flow, right? And the flow, remember, is going to go from left to right. So we have flow on the inductor, QL. We have flow on this first resistor, QR1. Okay. So QL and QR1 are going to converge, right? So they kind of get smushed together into one path right here at the junction. And then once the flow goes through the junction, the flow splits again, right? So we have flow that goes over R2, so we have QR2, and then we have flow into the capacitor QC. Okay. All right. So by conservation of mass, right? So this is the only sources of blood, at least that we can see, right? All the flow coming in has to equal all the flow coming out. Right? And so I'm actually going to apply conservation of mass right at the junction between here. Okay. All right. So the flow's coming in. We have two flows coming in. Okay. So for the flows coming in, we have QL plus QR1. Okay. And then the flows coming out of the junction is going to be QR2 plus QC. Okay. So you may be wondering, for this one, I think, just the geometry of this problem makes it a bit clear kind of where we should do conservation mass. There's one junction in the circuit, but I think as you do the homework, you may be wondering how to choose, or how do I choose kind of what junction to do. And the answer to that is that there's no straight answer. And so you can apply the junction wherever you think it makes the most sense. The only thing that you have to do, or the only thing you have to make sure, is that wherever you do apply the junction, QC is in your expression at some point. Right. So usually you're going to choose a junction that's close to the capacitor, just because that way you can isolate QC on its own. But whatever junction that you pick, the QC has to show up there somewhere. Okay. So if you use that kind of logic, that should help you kind of choose what junction to choose. Okay. Okay. So now that we have this expression here, let's plug in for the things that we can plug in for. Okay. So we want to replace the Q's here with the expressions from the circuit. Okay. Because what we have here is we have a perfectly valid equation here for conservation of mass, but we've kind of made up some additional variables here just to kind of help us, right? So in particular, we have QR1, QR2, right? And to an extent QC as well, right? QL is actually okay, because we already are solving for the flow on the inductor with this equation up here, right? So QL can stay the same, but everything else we want to replace it with either something that we're solving for, or something that's going to be given to us in the circuit, either the values of the circuit elements themselves or an inflow boundary condition. Correctly solving for. Okay. And that's true just for most kind of mathematical models in general, right? So it's not uncommon, and we're gonna do this kind of several more times in this class where, we have our equations, we have our model. We may create intermediate variables just to make it a little bit easier to conceptualize, it makes the work a little bit cleaner. That's fine. You can create as many intermediate variables as you can. But at the end, kind of when you present and when you're kind of ready to solve the equations, you should put it you should put your equations in terms of one, what you're solving for, or two, things that you're given. Okay. And so the things that we're solving for in this problem are either QL and PC. Okay. All right. So the three terms that I've circled in green right there, QR1, QR2, QC, they don't fit this criteria because these are all intermediate variables. Okay, so let's go ahead and plug in for these variables here. So QR1, same thing with QR2. This is a flow over a resistor. And we have we have an equation that governs our behavior on a resistor, which is Ohm's law. Right? Right. So Ohm's law says this, that the pressure difference across the resistor, so we have P up minus P down, is equal to the flow rate over the resistor multiplied by its resistance. Okay. Simple V is equal to IR, except the fluid mechanics version of this. So P is equal to QR. Okay. So if we solve for the flow, we just have to divide by the resistance here. So Q is equal to P up minus P down divided by the resistance. Okay. All right, so let's apply this equation to both of our resistors in the circuit, right? So let's apply this to R1. And let's apply this to R2. Okay, so let's look at R1. Okay. Let me go back up to the original diagram. Okay, so just like we did with the inductor, right? The game that we're playing here is we're going to determine what the upstream pressure on the resistance is and the downstream pressure, okay? So in this case, for R1, right, if we use our same laws here, where everything connected by a wire has the same pressure, the same voltage, right? We know that the upstream pressure on R1 is the inflow condition, Pi of T, okay? And then for the downstream condition, right? The pressure that's downstream on the resistance, we know that that's P sub C, okay? All right, so we apply both of these and we get QR1 is equal to Pi of T minus PC, all divided by R. And of course, we can plug in for Pi of T. We know Pi of T is 30 cosine pi T plus 90. So you can plug that in if you. All right, similarly for QR2. Okay. Let's go back up to the diagram. Okay. So we're going to find the upstream pressure on resistor R2 and the downstream pressure. Okay. So the upstream pressure on R2 is quite easy, right? Because it's connected by a wire to the capacitor. So the upstream pressure on R2 here is going to be P sub C, okay? The downstream pressure, if we follow this wire downstream of the resistance, we can see that the downstream side of the resistor R2 is connected to ground, okay? And remember what ground means. Ground basically means that we have a pressure of 0 there. Okay. And so we can write our expression for QR2. So QR2 is going to be P sub C minus 0 for ground, all divided by R2. So if we just simplify this, this is just PC over R2. Question, yes.
Yeah, why isn't PC a function of time?
It is a function of time.
Okay.
It's just that we don't know what that is explicitly because we're going to solve for it through our equation.
Okay.
Yeah. Mhm. All right, any other questions on how we got this, got these two equations here? Okay, so that takes care of QR1 and QR2. For Q sub C, the flow on the capacitor, we're just gonna directly plug in our governing equation for the capacitor here. All right. So the governing equation on a capacitor states that the flow going into a capacitor is equal to the capacitance multiplied by the time derivative of the pressure on that capacitor. So for the capacitor, there's not much we have to plug in. Okay. All right, so let's plug all these three in to our conservation of mass equation. Okay. All right, so our conservation of mass equation, we had Q sub L, the flow on the inductor. We're leaving that one on its own just because that's something we're solving for. That's what our other differential equation was. Okay. Plus, we have a flow on the first resistors. We have Pi of T minus P sub C divided by R1. Okay. This is equal to flow on the second resistor, which is QR2. So that's P sub C divided by R2, plus the flow into the capacitor, which we have right here, which is C dPc dt. All right. So we're almost there. We just need to simplify this a little bit. So let's solve for the derivative term. Okay, so let's solve for dPc dt. Right, so I'm going to subtract PC over R2 from both sides, divide everything by C. Okay, and what we get is dPc dt is equal to 1 over the capacitance multiplied by Pi of T minus P sub C divided by R1 plus UL minus PC over R2. Or again, you can plug in for Pi of T, but because we know that that's 30 cosine pi T plus 90, but I'm just leaving like that just for the sake of just for the sake of simplicity. Okay. All right. Any questions on how we got that equation there? Okay. All right, so let's take a look at the MATLAB implementation. Okay, so we have two equations here, right? They're a little bit more complicated than our last example. Where's our Q? Right here, right? So we have our two equations here. So let's look at how to solve these equations in MATLAB. Okay, and remember, we're using the package ODE 45, and so when I say that you need to write the MATLAB code for this, you're really just setting up ODE 45, and so you're setting all the variables, you're setting all the functions that's needed to run that tool. Okay, so let me go ahead and switch to MATLAB here. Okay, so let's look one at a time. Okay, so let's look at the equations file first. All right, so remember the way to set this up is that you need to create two MATLAB files. So one file is going to be for the equations and the parameters, okay, and the other file is going to be to actually run ODE 45. Okay, so I would start with the equations file just because that kind of just follows logically after you do the work by hand. And then you plug that into ODE 45 in the other file. Okay, so here is the file here, and I don't know why this is signed. It should be cosine. Okay, So I have these posted on Canvas for you, and so if you go on Canvas on week 7 right here, you can see that I've posted both of these MATLAB files, so you can use them as reference for the homework, okay? Okay, so first thing we're gonna do here is we're going to specify the parameter values, and let me just delete this for now, just because we're gonna do that with the tuning, just to make things a bit cleaner, okay? Okay, so you can see inside this function file right here, we have a variable here that tracks the inlet condition. And so this has the same value as our inflow condition, so 30 times cosine of pi t plus 90. Okay. Next here, we're specifying all of the values for the parameters. So all the circuit elements in our diagram here need to have values. So this is the value of the inductance, L. We have the value of the two resistances, R1 and R2. And we have the value of the capacitance here. Okay. Next, we're going to specify our two solution variables. And so our two solution variables is Q sub L. So that's going to be our first variable here, Y of 1. Then we have P sub C. That's our second variable here, Y of 2. Okay. And then finally down here, under dy dt, we are specifying the governing ODEs. Okay, so basically what we just saw for in our notes, you're going to write here, at least the right hand side, right? And so remember, the first equation here, dy dt at 1, this is going to be our first equation. So this is the equation governing the inductor. Okay, and we know it's the first equation because that's what we labeled it as. So we have QL is equal to the first variable here. Okay, and this right here is the equation governing the capacitor. Okay. And so if you read these out, they read exactly as the equations that we just derived. So the equation on the inductor, we have dQL dt is equal to 1 divided by L multiplied by the inflow boundary condition, Pi of t, minus P sub C. Okay. And then dy dt2, so that is dPc dt, or the time derivative of the pressure on the capacitor. This is 1 divided by the capacitance multiplied by Q sub L, the flow on the inductor, plus Pi minus Pc divided by R1 minus Pc divided by R2. Okay, so if you cross-reference this with the notes that we just did, you'll see that this is the same equation here. Okay, so that's the general setup for the equations function. So I have basically four sections here, and you're going to fill in each of the 4 sections depending on your.
If you have, say, like 4 total capacitor inductors, would you just increase the dy/dt matrix?
Exactly. Yeah. So let's say that you have 4 variables here, right? So let's say we have 2 more capacitors. So P1, or I guess this would be P2 is equal to Y of 3. P3 is equal to Y of 4. And then dy dt here would be 4. Right here. And then you have dy dt of 3 is equal to yada yada. And dy dt and 4 is equal to dot, dot, dot. Yeah, so you just kind of increase everything by, or 2, depending on how many equations. All right, any other questions on this file right here? Okay. All right, so the equation file, I think the setup for this is pretty straightforward every time. You just have these 4 sections, and so you fill them in. Okay. Now you come to the ODE45 file, right? So this is the file that actually runs ODE45. So you can see that we're calling the function right here. And so same thing. And so we're gonna specify basically every single section here. So we're gonna specify the beginning and ending time. So you can see that we're running this simulation for 15 seconds. So we're starting at a time of 0, and we're ending at a time of 15. Okay. We're specifying the initial conditions for each of the variables. So for each variable that you have, so for the flow on the inductor and the pressure on the capacitor, we have to set what their initial conditions are. You don't have to worry about this too much for our systems, just because LPMs are pretty stable, and so you don't have to worry about the initial conditions. So actually, what you'll see me do a lot is you'll see me actually initialize these at 0, and then we'll let them come up on them. Okay. Okay, next we have the ODE45 function, and so you can just for the most part copy this line exactly as it is. The only thing that you have to change here is the name of this function right here, right? And so. And so the way to use ODE45 is you're kind of inputting what's called it's called an embedded function. And so you want to make sure that you give it the same name as what you gave it in the other file, right? And so if you notice in the other file here, we defined our function, we gave it the name here. And so you want to make sure that this name right here matches what you pass into ODE45 right here. Okay. All right, and so from there it's just plotting. And so you can save the variables out, you can plot them, so that's pretty straightforward. So let me go ahead and run the code.
You have to change the matrix back to 2 to 1, the zero matrix.
Oh,
Yeah,
yeah.
you just,
I know.
right?
Ah, thank you. All right, so let's go ahead and run this code here. Gonna take a second. Right. And there we have our results. Okay. All right. So you can see here that when we have a sinusoidal inflow, right? So our pressure here was a sinusoid, our results here tend to look like a sinusoid eventually. And so for the flow on the inductor, you can see here that there's a little bit of an overshoot, which is kind of interesting. And then after that overshoot, it kind of settles into this kind of steady rhythm right here. Okay. For the pressure, it's a little bit hard to see, but there's kind of a ramp up period where this first section here is a little bit thinner, and then again it kind of levels out just to steady state. Okay. All right. And so to check your results here, for the most part, I think for the homework I only gave you sinusoidal inputs, so you should be getting sinusoidal outputs if you did everything correct. Okay. All right. Any questions on this? Okay. All right, and so that's step 1 and step 2 of these problems, right? All right, let me bring back the iPad here. Okay. So we've now solved these equations in MATLAB. Okay. But there's one step that I kind of glossed over, right? And that was the values of our circuit parameters. And so the inductance, the resistance, and the capacitance. Okay. So we kind of chose those parameters kind of random, right? Well, for you guys, from your perspective, it was random, but for me, I actually tried it out a bit. All right, so that kind of begs the question of how do we actually choose these parameter values, right? So how do we set these? Okay. Because their values are going to be really important because what you'll see is that the values for these parameters actually have a very strong influence on the results in terms of the plots that we're going to generate, the flows and the pressure that we're going to solve for. So the way that we choose these is kind of a little bit of a backward, I would say backward methodology than probably what you guys are used to, because usually when you have a problem that has parameters, right, and these parameters represent physical quantities, so either geometric or material properties, these are things that you typically plug in at the beginning and then you solve for your solution. Okay. When you have a situation like this, where you have a model, right? Your model is somewhat simplified. It doesn't kind of represent the whole thing. And so computing values for these parameters is not 100% straightforward, right? This is not something you can just kind of look up in a book, right? We do have a formula for the resistance, and so the resistance is a little bit of a unique thing. So we do have a formula for that we obtained from our steady flow fluid mechanics review. But the capacitance and the inductance, because they're so lumped, they kind of lump together such big, such complex quantities. There's not so much a straightforward thing. Okay. And so in these situations, instead of the solution being the goal, it kind of flips on its head. And so in these problems, finding the right parameters actually becomes the goal. Okay. So this type of problem is known as an inverse problem. Okay. So an inverse problem is basically, solving for the most appropriate or solving for the best parameters to a model that fit a certain result. Okay. For those of you who were in 454 with me last semester, this is basically the same thing as an optimization problem. But we're not going to do optimization. We're just going to do guess and check. And so, a much more kind of a little bit of a caveman method, but a very effective one in this case. Okay. Okay. So what is the result that I'm talking about here? Well, when for an LPM model, right? What we're solving for essentially are flows and pressures essentially within the cardiovascular system. Okay? Okay. That's our goal, right? So to solve for these things just because it's hard to measure them, right? In particular, it's not just any cardiovascular system that we're solving for. These are quantities that are specific to a patient, right? And so it would be best, right? It would be best if we could tune our model parameters or set their values so that they fit a person's physiology, it fits a person's data as closely as possible. All right. Because for any given patient, right? And so, and of course I'm thinking ahead right now, right? So I'm thinking to, some vascular and cardiovascular modeling, right? So whenever you have kind of a CT scan done on someone, a CT scan is kind of the minimum that you need to construct a vascular model, right? Usually what comes along with it is a host of kind of medical tests, right? At the very least, they're going to take your blood pressure in the lab. They're going to take some blood samples, right? They're going to measure things like your cardiac output. They're going to measure your heart rate, things like that. Okay. And so we want to make sure that our parameters fit as much of this data as possible. Okay. All right. So for example, let's take our previous circuit and let's tune it to certain individuals. All right. So let's look at this. Let's look at this parameter set first. Okay, so we'll call it parameter set A. Okay. So let's look at an inductance of 0.25. Let's look at a resistance R1 of 1, R2 also 1, and a capacitance of 0.075. Okay. So that is a set of parameter values that we're going to test. All right. So let's go back to our code and let's run the code with these parameter values and see and kind of observe the results. Let's see what we can get. Actually, let me leave that. Okay, so let's come back to MATLAB. Okay, so we're back at the code here. So let's go back to our parameters file here. So, right. So remember in this parameters file or in this file here, I have values that you can set for all the parameters here. Okay. So for them to match kind of what we just set in the notes, we're going to set R1 equal to 1. We're going to set R2 is also equal to 1. Okay. The inductance here is 0.25 and the capacitance is 0.075. Okay. So let's run the code and let's observe what we can see from the results. Okay. And this is kind of an important point too, that these simulations here are necessarily unsteady because we have an unsteady inflow, right? And so when I say observe the results, what I mean is to observe kind of the steady state results. And so there's always going to be a period of time where the model's kind of ramping up. So we're going to ignore this portion here and focus on when the model here is steady state. Okay. Okay. So let's look on the flow through the capacitor. In fact, let me kind of zoom in on this area here just to make it a little bit easier to see. Okay. And let me go ahead and draw a line here that represents kind of the mean. Okay. Okay. So you can see from this diagram here that we have our flow is oscillating, right? And so our flow through the inductor is going up and down, but there is a certain average value that it's averaging between. Okay. And that average is roughly about 90 milliliters per second. Okay. That's the mean flow. Okay. Let's do the same thing for the pressure. And so for the pressure, let me go ahead and zoom in. Let's take the last two peaks here. Okay. And we go ahead and draw on the average. And so the average, well, in this particular case, it just happened to be 90 for both, although that's kind of uncommon. And so the average pressure on the capacitor is about 90 millimeters of okay. Okay, so that's the first thing that you should note whenever you're kind of looking at your LPM results is to see what the averages are. Okay. The other thing that we can look at here is what I call the peak to peak amplitude. Okay. Or the way I usually define it as the magnitude from the mean up to the peak. Okay. And the mean to the trough here. Okay. And so in addition to the mean value here, what I also like to mention here is just the max and min for the waves. Okay. So you can see the max here is somewhere in the ballpark of maybe 107. Okay. And the min somewhere around the ballpark of 70, 73, 72. Okay. All right. And then for the pressure, the max here is just north of 110. So this is maybe 112. And then for the pressure here, we have a nice one close here. That's about 60, 68. Okay. Okay. So let's note this down. So let's go back to the notes here and let's note down the means and the max and min. Okay. So let's stop here. Let's go back here. Okay. So with this setup here, we have a mean flow. Of around 90. And everything here is in CGS units, right? So you have a mean flow of about 90 milliliters per second. We have a mean pressure of about 90 millimeters of mercury. Okay. Usually I just note the max, and I assume that it's kind of the same difference between the max and min. So the max flow was, oh shoot, I forgot already. It's like 107 milliliters per second. And the max pressure, somewhere around 112. Okay. So what we have here on the left here is these are, I consider these the input parameters. Okay. And on the right here, we have the model results or model outputs. Okay. So the way to kind of look at this is that, whatever you choose for the input parameters is going to influence your model outputs, okay? So let's say, right, so this is the model that we have, but let's say that our patient the one that we're simulating has a cardiac output of 40 milliliters per second. A mean pressure of about 90 millimeters of mercury. And a maximum pressure of 110 millimeters of mercury. Okay. And we want to set the model parameters to match this as closely as possible. Okay. Okay. So let's look at our model outputs here, and let's look at our targets. Okay. So let's start with the mean flow rate. So we know the mean flow rate here is 40 milliliters per second. Okay. If we compare that to what we're getting right now, these are pretty far off, right? So the mean flow rate, we need to fix that. We need to adjust that. Okay. All right. Similarly, so for the pressure we're aiming for here is 90 millimeters of mercury. So for the pressure, we're actually pretty spot on, right? So the pressure we don't need to do anything for the pressure. But what you're going to see is that when we try to fix things for the flow, it's going to affect the pressure as well. So it's kind of balancing. Okay. Max pressure of 110, we're pretty much there. And so, we're at 112, we're pretty close in that sense. Okay. All right. So we need to basically reduce the amount of flow that's coming into our system. Okay. In other words, or to be more specific, we need to reduce flow through the inductor. Okay. All right. So to reduce the flow, we'll talk more specifics in terms of, the intuition that you can use to tune the parameters, but in general, if you want to reduce the flow, or, let's say that you have an electric circuit, you want to reduce the amount of current going through the circuit, right? Intuitively, the thing that you probably want to do is you want to increase the resistances, right? So if you increase the resistance with a fixed inflow or fixed kind of inlet condition, that should reduce the flow that's coming through. Right. The other thing that we'll do, so I actually do this in 2 steps. Normally, when you're tuning parameters, you typically only want to change one thing at a time, right? That's the benefit of working with a computational model like this, is that when you change one thing, you can run the code right away and you can kind of see the outputs, right? But just for the sake of time, I want to make sure I finish this today. I'm also going to increase the inductance as well. But let me make a note here. So normally, you only want to change one thing at a time. Because once you have your MATLAB code set up, once you have your LPM code set up, it's very easy to change one thing, run it, see what happens, and then you can kind of do things from there. Okay. Because what you're doing in your mind, and so you're kind of building kind of an intuition for kind of what certain parameters will do to your model. Okay. The fact of the matter is that every LPM behaves a bit differently. So we'll talk about kind of just general behaviors in a second after this. But for every LPM model, for every, and this isn't true in general, for every kind of CFD model, any kind of analytics that you do in a computer, right? You're kind of building kind of a model in your head for how this system behaves. And so the only way that you can really do that is just change one thing at a time, see how that affects your results, change another thing, see how that affects your results, right? And then slowly, as you kind of do, just by pure trial and error, and just by pure kind of brute force, you start to get a sense of how your model is behaving and how it's going to react to the parameters. Okay. And if you start changing kind of more than one thing at once, so let's say you change the resistance and the inductance, even if you think you know what you're doing, oftentimes it kind of results in, and things changing, and you kind of get the wrong impression, and overall it probably takes you longer to kind of tune them up. So I definitely recommend changing one thing at a time, unless you're getting a lecture on this and you have 10 minutes to cover everything else. So that's the only situation where you can change more than one thing. Okay. And so with that note, let's go ahead and change these. So let's say that we're going to change our inductance to 0.75. Let's change our input resistance, or the first resistance, to 5. Let's change R2 to 2.25. And then we're going to keep the capacitance the same. So we're going to keep the capacitance 0.7075. Okay. Okay, so let's go ahead and bring MATLAB back. And so let's see how this looks. All right, so let me go ahead and close these. Okay, so let's go back to our parameters here. Let's go ahead and change these. So let's change the inductance to 0.75. We'll change the resistance to 5. And R2 will change 2.25, excuse me. And so let's go ahead and run our code and see what this looks like. Okay, remember, we're aiming for a mean flow rate of around 40 and a mean pressure around 90 with a max pressure around 110. Okay. Okay, so once again, let me go ahead and zoom in here on just this part of the, this part here, okay? It's a little bit scuffed here, I kind of missed the box, but let me move it up here a bit, okay? Okay, and so with this change right here, we can see that our mean flow rate is right at around 40, so we're kind of right on the nose here, so that's good. Okay. Next, let's look at our pressure on the capacitance, okay? So once again, let me zoom in on this part right here. Okay. Let's look at our mean pressure. So our mean pressure is just whatever is kind of right in the middle of these peaks. And so we can see here that our mean pressure is right at about 90. It may not be exactly 90, but it's pretty close. Okay. And then our maximum pressure here, if I could draw a straight line, is 110, maybe a tad over 110. So we may be at about 112. Okay. And so, that's what it means to tune the parameters. And so, usually for a tuning problem, you'll be given the results that you want to obtain. And then it's up to you to kind of tinker with the parameters, kind of trial and error them until you get the results that you want. Okay. All right. Any questions on this? Okay. All right, sounds good. All right, so for the last few minutes today, I want to talk about kind of just some general kind of rules of thumb for tuning LPMs. Okay, because even though a lot of tuning is trial and error, it's good to have some rule of thumb. So you're doing more than just changing things randomly and seeing what works, right? There should be some guiding principles that kind of tell you what to do. Okay. Rules of thumb. Right, so I have two of them here. Right, number one, the first thing that you should tune in an LPM are the resistors, actually. And so the first rule of thumb here is to tune the resistances to set the mean pressures and mean flow rates. So in general, for a circuit like this, right? When you talk about mean quantities, you're talking about kind of time average quantities, right? Or things that don't change with time. Out of all the circuit elements that we've considered, the resistor is kind of the only one that doesn't have a differential equation, right? And so because of that, the resistances kind of do a great job of setting your mean values, okay? The inductors and capacitors, they do have an effect on the mean values slightly, but the main things that are going to affect your mean pressures and mean flows are going to be the resistances, okay? And your guiding light, or kind of the thing that's going to give you intuition here, is going to be Ohm's law, right? So our Ohm's law here is that pressure is equal to flow rate times resistance. Okay. So even though there are multiple resistances in your circuit, right, there is a notion, or there is kind of a concept of a total resistance, right? And so the more resistances overall that you have in a circuit, the more resistance the whole circuit has, right? And so you can use this methodology here. So let's say that in the past example, right? In the past example, we know that we needed to modulate the flow, right? And so if we look at our Ohm's law here, right, we know that flow is equal to pressure divided by resistance, right? Right. So since our last problem, we had a fixed pressure, right? Our inflow condition with pressure. And so in that sense, the inflow condition was basically set. There wasn't really anything we can do about it, right? If we increase the resistance, if the pressure is more or less fixed, right? If we increase the resistances, the only thing that can change in this relationship is the flow. Okay. Right, and then the opposite is true as well. So let's say that you have a circuit with an inflow flow. So we have a QI of T, right? So your flow rate into the system is fixed. If you wanted to modulate the pressure, so change the pressure to be up or down, the mean pressure, you would change the resistance, okay? And your whole key to this whole operation is ohms law, okay? All right, so that's the first thing you should do. So just because there's a linear relationship between the resistances and the flows and pressures, that's always the easiest thing to start with, is the resistances. Okay? Number two, once your resistances are set, then for the most part, you can kind of leave them alone. So step two here is to tune the capacitances and inductances. Okay. And what the capacitances and inductances, what they're going to mostly kind of modulate here are the peak to peak values, and so the amplitudes of the waves. And so in the homework, what you're going to see is that, when I ask you to tune the circuits, on the one hand, I'm going to have you tune for certain mean values, right? So certain mean flow rates, certain mean pressures, and then I'm going to ask you to tune for a certain maximum pressure or maximum flow, okay? And so whenever you see maximum or minimum, that means you should tune the inductors and capacitors to do that for you, okay? In particular, I'll give you an extra hint. So, for particular flows and pressures, remember that when we're setting up our differential equations, we're setting one up for each individual capacitor or inductor, right? And so when I ask you to adjust the mean or the maximum flow on a certain inductor, you should probably change the inductance on that inductor. Kind of, that's kind of where you should look for that. Okay. Now it's all coupled, so adjusting a capacitor that is going to affect the flow rate on an inductor to kind of an indirect degree. But if you want a direct effect on it, then I would adjust the element or the parameter that's directly affecting that particular element. Okay. All right. Any questions on any of this? Yeah.
But then the goal that's like, doesn't matter what you change, as long as this is the final result, the only thing that really matters.
Yeah.
As long as it's modeling correctly.
No, that's a great question. So that's kind of a question of kind of model uniqueness. And so, there's a lot of research going into that where, you can get, depending on what your results are, what you're looking for, there may be more than one unique solution to get those. And so I would say that's still kind of a research thing. But for this class, the solution should be pretty unique because these circuits are they're not that complex. But when you get to more complex circuits and kind of more indirect data, the kind that you mostly see in the clinic, then it's a good question. Question.
I was gonna say, you said change the resistance to start checking values.
Yeah.
And there's a specific order. Say you have 3 resistors, would you check them in a certain order or just?
Generally speaking, the ones that are downstream, actually the ones that are closer to the ends, those have a stronger effect. But it depends on which flows and which pressures that you're looking at too. And so I would start. So let's say that you're tuning for a pressure on a certain capacitor. I would tune the resistances that are close to that capacitor to try to get that result. But in general, the resistances that are downstream actually affect the results more. Yep. Yes, but it's going to change for everyone. So all the resistors have an effect, and so I would kind of tinker with it. But that's kind of the general way. All right, any final questions on this? Okay, that's another issue. Okay. All right, so we'll meet up again on Thursday. So thank you guys for coming today. Hope you guys enjoy the rest of your afternoon, and rest of the evening, and I will see you all on Thursday. Okay, Andre, so the co-host is me, so I'm not quite sure kind of so my co-host is on I'm logged in here on my computer and on my iPad. I think this is the first message I've gotten to you all semester. Are you enrolled in the class? Okay. So I earlier in the semester, I think I requested the department to issue permits for people on the wait list. And so did you get that email earlier this semester? Unfortunately, the time has passed, and so it's kind of way too late now to add any students to the class. And so you know, I mean, at this point, I'm not sure what to say, but you know, I mean, I think this class will be offered again next year, and so you can try to pick the class next year if you want. Okay, then I'm not sure what may have happened then, but I mean, but right now, you know, there's not really much we can do at this point, because we're in week 7 already.
Was it Diego?
No, that was Dylan. Dylan.
I can add you to the canvas, but I can't give you a grade for the class because you're not enrolled in it. And so if you just want to follow along just to audit the class, you can do that, but I can't add you to the class. Yeah, if you just want to audit the class, that's fine, but we can't officially enroll you, and I can't give you a grade for the class. So just so we're clear, so I can add you to the class just for your own, I can add you to the canvas just for your own interest, but it's if you're not actually taking the class. So, you know, I'm not gonna grade any of your material. I'm not gonna, you know, I'm not gonna give you an exam. This is just for your own interest. Great. Okay, yeah, so go ahead and send me an email. I can add you to the Canvas site. I can add you manually to the Canvas site, but yeah, it's too late to enroll. Okay. What's up?
I have just some curiosity questions about kind of like the way like we're able to use circuits for one parameter. Is it like the only reason we're able to do that is because like of the kinetic energy like in the system? Like you can model like any system has energy like as a circuit. Kind of like heat transfer or
Kind of. It's more things that flow.
things that
And so if you want to get really specific, you know, there's if you read up kind of potential theory in math, and so if anything that has kind of something called like a potential function, and so you're kind of on the same you're in the right ballpark. So anything that you know, you measure, you know, difference of one thing is equal to the flow of another thing. So, you know, like circuits is like that, difference in voltage is flow rate,
difference in temperature for heat.
Exactly.
Okay. And
Exactly.
Difference in pressure.
Exactly. So anything that has that kind of concept, you can model with the circuit, just because circuits were kind of built on that methodology.
Okay. And then like kind of like how, you know, like for current goes like in the path of least resistance.
Yeah.
So I guess like in this case of the capacitor like has like less resistance than the resistor. So it's gonna like, for in case of cardiovascular system, it'll want to expand your vessels before it starts driving the flow forward.
Kind of. It's gonna do both at the same time.
But it would like prefer like it would like resort to expansion first.
Yeah, it depends on the capacitance. And so the capacitance, it doesn't have a direct resistance, but it has something called an impedance. And so it has a resistance. It's just the way that we measure it is a little bit different. We're actually gonna go over impedance later on.
Yeah, I remember covering impedance in circuits. It's like an internal resistance.
Yes, yeah. And so we'll talk about that a bit too. So there will be kind of an impedance for the capacitor, and it kind of determines which way the flow goes.
Oh, okay, that makes sense. That's okay for sure. That's all I have.
Yeah.
Thank you.
Okay, I will send you, an invite. Yeah, after, I'm teaching another class right now, but I'll write your email down and I'll send you an email, later today.
Yeah, that's,
Yeah,
your office hours is Thursday, right?
yes, my next one's Thursday, 2:30 to 3:30.
Okay, Thursday. Okay, just because I want to talk to you about the assignment from Friday,
Okay,
because I missed it, but like I was having so many issues with that.
okay,
And I wanted to go to the office hours and stuff, it's just, I wasn't feeling good.
Okay.
For that, so
Okay.
I wanna.
yeah, let's
see,
talk
'cause-
Thursdays then.
Okay, yeah, thank you.
Okay, yeah, I'll send you an email, later. All right, I gotta sign up. I gotta.